Okay guys, now we're going to involve some calculus with these problems. Hopefully you notice some exponential equations. You go ahead and graph these on your notebook or on a piece of paper, okay? Alright, so notice that these are all exponential equations. I'm going to label the y-intercept for the original exponential is 0, 1. This exponential right here has got a vertical stretch of 3. So the y-intercept of 1 now becomes 3, 0. Horizontal asymptote still the x-axis. This one's got the vertical stretch, but also a horizontal compression. However, the y-intercept and horizontal asymptote remain the same. 0, 3, still the y-intercept. And then this is the general form, alright? What you've seen in pre-calculus. PERT is the principal, and it just looks like the previous problem. Same format. With a y-intercept of 0p. And in this course, you're actually not going to see it as PERT, you're going to see it as y equals c times e to the kt. Alright, so when you make that sketch, this is going to be the same idea with 0c as the y-intercept. Alright, cool. Now let's do some calculus with that. We have already sketched all the functions. Letter B says solve for y prime, which is the derivative. Alright, so the derivative, well, let's skip this one right here. I mean, let's do it right here. Y is e to the t, therefore y prime is itself, e to the t. And what I'm trying to say for letter C is y prime equals y. Notice how those are the same, so y prime equals y. Okay, now let's do it for this one. Y equals 3e to the t. I'm just going to rewrite the function. What's the derivative of just that part? E to the something is itself times 3. It's the same, so y prime is 3 times e to the t. What I'm trying to point out again is that this is the same as that. Therefore, letter C, rewrite it in terms of y prime. We're going to say that y prime equals y. Pretty cool, huh? We can rewrite the derivative in terms of a variable. Okay, next one gets just a little more advanced than that due to the horizontal compression. I'm going to rewrite the equation. And y prime is the function. But look, now there's the inside function. What's the derivative of that inside function? Times 2. Times 2. I'm going to write it like this instead of 6. Because what I'm trying to point out is that this is the same as that. This is the same, so therefore y prime is the same as 2 times y. This is y, this is 2. 2 times y. Okay, looks a little better, right? Alright, this one right here is the general form. Y equals p is a constant e to the rt. The variable is t in this case, alright? Treat every other p, e, and r like they're numbers. T is the variable we're differentiating with respect to. So y prime in terms of t is going to be the function times the derivative of the inside, which is times r. And then this can be written as y prime. Again, this is y. Therefore, it's r times y. Wow, that's a big idea for this course. Alright? And in the general form, in the other format, remember these two are the same, it's just different variables they're using now. Y prime is c times e to the kt. The function's in terms of t, so times k. And again, this is y. That's y, that's y. So therefore, y prime is k times y. That's what the textbook will show you, alright? The derivative depends on a variable y for all these examples, but also a constant. So it's y times a constant, y times the constant r, y times 2, or y times, in this case, 1. Okay, they all follow the same format. The derivative is some constant, some number times y. Alright, for all these exponentials, look at that. Cool idea in this pattern. Alright, and what I want to do on number 13 is just highlight that idea, re-emphasize it. This is the definition. If you ever see this on a calculus problem, I want you to know it in both ways. This means derivative. Y prime is derivative. This is also derivative. So if you see this, you should immediately think this, ky. These two are the same. Some constant times y. Okay? And if you see it in that form, I want you to think it's some constant r times y, because they use those interchangeably. Alright, so these are the symbols. Now in words, here's how you will see it in words. So please write down the symbols first. And then in words, you're going to see this stands for the rate of change. Alright, so dy dx stands for the rate of change. We're going to see the rate of change In words, we will say the rate of change is directly proportional. I'll explain what that means. Directly proportional. You will see this in a lot of word problems. To the y value. And I kind of touched upon this already. This means the derivative depends on the y value. And this phrase right here, directly proportional, what that implies is that the y value is being multiplied by some constant k. Or the y value is being multiplied by some constant r. That's what directly proportional implies. In a word problem, you're going to see directly proportional to a population. The y value will stand for a population. Or it could be directly proportional to the amount of money, if y stands for the amount of money. Okay, so they're the definitions for these exponential equations. If it's some constant times y, then by default, you know it better be an exponential equation. All right, or if you read this phrase, the rate of change, meaning the derivative is directly proportional to a y value, this implies already exponential equation. Okay, next, let's see this in the context of a word problem, like the ones we've seen before with these tables. This is number 14 on the notes, and I abbreviated a little bit, but it says something along the lines, bacteria in a dish with a rate of change proportional to a constant k. Again, when we see this, we should immediately think exponential. For this problem, just because it's the notes, I'm giving it to you. But in a word problem, this won't be given to you. You are supposed to extract that from reading this statement. All right, so we're going to write it in the form c times e to the kt, but I prefer personally to write it as y equals a times b to the t. It's a little bit easier using this table from the examples that we did before. All right, so I'm going to start with that. Y equals a times b to the t. Let's identify a. What's the value of a? Is the initial one, 5,000. So then y is 5,000. What are we repeatedly multiplying by? If you notice, what's happening to the 5,000? It's being multiplied by a half. Multiplied by half. How many number of days or hours did it take? It took 4 hours, so I'm going to say t over 4. This is what I explained on the previous video, and you can easily do that using algebra. So far, we haven't used the calculus, but I'm going to show you the calculus in a moment. I still believe this method's easier. And from here, we can go to the other form, which is c times e to the kt. The way I did that, and I'll show you again, I explain it like this. I usually start with, all right, we can rewrite 2 as e to the ln 2. That's the same as 2. How can we rewrite 3? 3 is going to be the same as e to the ln 3. How can we rewrite 5? 5 is going to be e to the ln 5. All right, so how can I rewrite this base of 1/2? 1/2 is going to be e to the ln 1/2. But I don't just want 1/2. I want 1/2 to the t over 4. 1/2 to the t over 4. Well, remember, this is already that, e to the ln 1/2. If you put the t over 4 right there, that looks a little bit weird. It's not incorrect, but the property of logarithms we're going to use is this exponent will become the coefficient of that log. So I'm just going to rewrite it right there, okay? It's t over 4 right here. So 1/2 to the t over 4 is the same as this expression right there. Therefore, we can say, all right, 5,000 is the same. And this right here gets replaced with this down here, which is times e to the t over 4 times the ln of 2. All right? And that's almost precisely in that form. It's almost precisely in that form, so I'm just going to rewrite this a little bit different, but this is sufficient. You can stop right there. This is going to be the same as 5,000. Just for you to be easy, for it to be easy to identify the k value, I'm gonna separate this t. Notice how it's k times t. So I'm gonna separate. It's really e to the 1/4 times ln of 2. This is the k value times t. All right. This is kt, e to the kt. So that means that k is 1/4 ln of 2, all right, which is sometimes, I didn't ask it here, but a lot of times the question on the exams will be, what is the value, the growth factor of k? So that's another way of easily identifying it without using any calculus. All right, so that's letter A, and again, this is just a reminder, you don't have to do this every time. If you recall it, letter B You might need to use calculator for the next two parts. Definitely for letter C, probably not B. Letter B asks, how many bacteria are in the dish after 8 hours? This implies that T equals 8. T equals 8, then we're going to do B of 8 onto our new equation that we came up with, which is 5,000 times 1/2 to the, it was 8 over 4 because it was T over 4 originally, and 8 over 4 is just 2, so this is 1/2 square. 5,000 times 1/2 square, which is dividing by 4, which we get after 8 days, we should get 1,250 bacteria in the dish. Alright, check your work in the calculator. And then letter C, again, it's a problem. It's an algebra problem in my opinion. It says, when will the dish have 400 bacteria left? Now that means that this is B of T. B of T is 400, and we're going to solve that equation. So 400 is equal to 5,000 times 1/2 to the T over 4. Alright, we're going to divide, because we want to solve for T, we want to isolate, divide by 5,000, not isolate T, divide by 5,000, we get, I'm going to simplify it, 4 over 50, which I think can also be written as 2 over 25, equal to 1/2 to the T over 4. One of the strategies I've shown you is you can solve it from here. It's going to be ln of this fraction divided by ln of that fraction, okay? We're going to plug that in the calculator. Whoops, let me leave a little bit more space there. ln of 4 over 50 divided by ln of 1/2. But be careful, we want to do one more thing. We want to undo dividing by 4. How do we undo dividing by 4? Multiplying by 4 goes on the numerator. When you enter this in your calculator, go ahead and do that. I'm going to use the first 3 decimals or so. We get 14.5754 ... number of days. Or number of hours, whatever T stood for. I think it's hours in this problem. It's about 14.5 hours, a little bit more than 14.5, for the population to go from 5,000 to 400. Alright, if at this point you feel really good about what I've shown you in this video, this is pretty much what a sample exponential growth free response problem might look like on the AP exam. And if you feel great about doing it without almost any calculus, go right ahead. And you may stop watching this video now. However, because this is a calculus class, it's kind of my duty to show you how to do this problem as well by using calculus. So I'm going to do that next, even though I think the way I've shown you right now is way more efficient, and I'm going to show you the calculus way anyway, just so you see how much time this whole process can save you. Alright, so continue on if you're curious, or if you just want to learn the calculus way anyway. I'm going to flip the page, and I have the same problem written down. But again, I'm going to show you the calculus approach, and in my opinion, like I said, the algebra way might be the easiest of the two. Alright, so letter A. Normally they would, like I said, they won't give you the form y equals c times e to the kt, and they will not give you y equals a times b to the t. That's up to you to extract from this information. Remember that we have pulled this from directly proportional. Once we saw that directly proportional, we're allowed to write this, I'm sorry, y prime. The derivative is directly proportional to some constant, and the nice thing is that you don't have to show the work. If you remember that this means y equals c times e to the kt, the AP exam will give you full credit for that. You can go directly from here to here without showing any work. But you at least must remember one of these two. If you can remember this or recognize that to mean this, then you're in trouble, and then you would probably have to start from scratch. So let's suppose you did forget that on the exam. How would you do it then? Then you would start with a differential equation. dy dx is k times y. And then I've shown you this in the notes before. In differential equations, we do separate and integrate. That's what approach we're going to take here. So I'm going to separate dy with y and k with dx. Oh, it's dt. Let's use dt. That's what we've been using. Let's say d dt instead of d dx. And k dt. Alright, good. So now we're going to integrate both sides with respect to, this is in your notes by the way, I've done this with you before, but let's do it one more time. Good practice does not hurt. Antiderivative of 1 over something is ln of absolute value of that something. And on the right side is a constant. What's the antiderivative of any constant? It's the constant times the variable. The variable is t, so k times t plus some constant of integration. I'm gonna call it little c. All right, and this is ln. What's the implied base for ln? It is base e. So I'm gonna say base e. The exponent is the whole right side. Properties of logarithm say this is the base. This whole thing is the exponent. The base is e. This is the exponent. So let's rewrite it that way. I'm gonna say that absolute value of y is e. Remember, that's the base. The exponent is kt plus c. And the plus is part of the exponent. When do we add exponents? For what is the only case that you remember doing that? Whenever we're multiplying their same base. So kt times e to the c. And here's a crucial point in this method, because e is not a variable, c is not a variable. This is a constant, and that's a constant. We have a constant raised to another constant. What do we get in return? We get another constant. This constant, I'm going to call it capital C now, okay? And move it to the front of the coefficient. So capital C is right there. And we're left with c times e to the kt. And I told you guys, you've seen that before. And then to remove the absolute value, we're just going to say plus or minus. That just means the exponential is either a positive or a negative version of that, okay? Exponential equation. There it is. If you don't remember that, you can always use differential calculus to get there. But you're allowed to skip all this work if you just know that this means that. And the question is, how would we get k and c if you forgot to use the algebra that I've shown you before? Well, we got to plug these given values in, all right? So it says that t, we have values for t, and remember, this is y. This implies y values. So we have values for y and we have values for t. Let's plug them in. When y is 5,000, t is 0. So 5,000 implies that we're going to have c times e to the k times 0. K times 0 is just 0. And what's e to the 0? That's 1. 1 times c, this better just be just c equals 5,000. And we knew that from the previous problem. That was pretty easy. That's the beginning amount. So c is 5,000. And now we got to plug this point in to what we have next, all right? So now y is 2,500. 2,500. From the previous part, we determined that c is 5,000. So we're going to plug it in right there. 5,000 times e to the k, but t is now 4. K times 4, or 4k. E to the 4k. And now we got to solve for k. That looks a little familiar to me. Dividing both sides by that gives us, by 5,000 gives us 1/2, equal to e to the 4k. We got to solve for k, so let's take ln on both sides. ln of 1/2 equals 4k times ln e. Alright, remember that the exponent can become the coefficient of the log. And this is just 1. 1 times 4k, that means that k equals 1 over 4 times ln of 1/2. And that's what we obtained. That's what we obtained in the previous method of thinking about it, using algebra. Okay, there it is. Look at that. Letters B and C will be solved in the same way. So that's the end of this video, and I hope you like this exponential exploration as much as I did.